So before you need to learn about electric circuits, you need to kind of get one thing under your belt, and that's understanding circuit diagrams, because they're really important. They show us how circuits are built, and it's how they're used, what they're used in textbooks, and how you'll draw them in the exam and things like that. And what you can see here is a really bad drawing of what you may think a circuit should look like if someone who can't draw is drawing it. You can see a light bulb kind of here, a battery here, and this is a resistor, but you wouldn't be able to tell that from the drawing here. Now, I'm sure you can see the problems already with this diagram. It's kind of difficult to draw if you're not an artistic genius, and it's quite confusing, like where do the wires go, what connects to what. It's much easier if we have a more simple version of a diagram to help us build this circuit. So, instead we use circuit diagrams, which follow a few conventions. Now, the first thing is that we always use symbols, so I'm going to put my battery up here for this one, because usually a battery is at the top of a circuit diagram. So this is the symbol for a battery. We also need to have a symbol for the bulb, which is down here. And then a resistor, which is actually, this is the circuit symbol for a resistor. Now, already this is easier to understand because you're not trying to just interpret what this is and what this is. The wires, we don't just draw them kind of like wiggly lines. We always draw wires for circuit diagrams in straight lines, and that just makes it a lot easier to see. So as you can see here we go, nice straight lines. It's usually in a square kind of fashion. And then it's much easier to see what wires go where and what connects to what. So the two really important things to remember from this is that they should be square with straight lines, and that we use something called symbols, well, circuit symbols. Now, there's quite a lot of circuit symbols, but you don't need to know them all. But there are a few that it's really important that you do know, and they are these ones here. So, we start with a wire. A wire is just any straight line. That's all we do for a wire. If you see that, it means it's a wire. A cell is one battery, as you might think. We use the word battery and cell wrong in real life. A cell is kind of a singular, and then a battery is if you have more than one cell. So battery is two or more, it's the plural. So a battery would look something like this, and often they join it with dotted lines like that, or a straight solid line, it doesn't matter which. We then have a switch, and a switch looks something like this, which is kind of quite self-explanatory, and you can see that when the switch is closed it means it's a full wire, and when it's open it's broken the circuit. A bulb, as you saw me draw before, looks like this, but you may also sometimes see this symbol, and it's about two different types of bulb, but don't worry about which is which. A resistor, as you mentioned there, is just a straight square. A variable resistor, which you may have used in school, it's got a slider and a long coil of wire, and it's sometimes called a rheostat. It looks like a resistor like this, but with an arrow, and that arrow just means that you can change it. A motor, we're getting onto the ones now where they're quite self-descriptive in a minute for these three. A motor is just an M in a circle, so really easy to remember. An LDR, which is a light-dependent resistor, is another resistor symbol, so like this, but because it's light-dependent we have two arrows here, like this. And sometimes you might see it all in a circle. That's not necessary. So this is a light-dependent resistor. A thermistor, once again it's another resistor, so we have the straight line, but then we have a line like this and like this. I'm not exactly sure why they made that symbol, but this is what a thermistor is, and that's a resistor that is sensitive to heat. And then we have two nice, really easy ones, an ammeter, which is just an A in a circle, and a voltmeter, which is just a V in a circle. So some of them are really easy to remember. If it's got the word resistor in it, or ister, make sure you've got your resistor symbol with an arrow of sorts or something over it, if it's not just a bog standard resistor. Remember that a battery is one or more cells, and that a wire is simply a straight line, and that there's two symbols for bulbs. So that's all we really need to remember. If you know all of those, you're sorted. The rest would be explained to you in an exam if you necessarily needed them. Now, some circuits won't flow. Some circuits just don't work. If I draw a circuit that looks like this, you could probably recognise that this wouldn't work because the circuit isn't complete. A circuit needs to be complete for the electrons to flow, and that's something we'll come on to in the next section. But this would not work. If I added a line in here, now it will. So a circuit and a circuit diagram has to be a complete loop. That's really, really important. Complete loop. That's how a switch works. So basically a switch, we have our really quick circuit, and you can see how quick they are to draw by how easily I'm drawing them, and a switch here. Now the switch is broken when it's closed, not broken, open. When it's closed, we complete the wires, we make that into a complete circuit, which is why the electrons can now flow. Make sure though you never draw a circuit or build a circuit that looks just like this, with all it's got is wires and a battery, because this is called a short circuit. And if you've ever done the FET simulation, and maybe in a computer lesson, you'll see that it kind of all sets on fire. It probably won't happen with a battery, but it doesn't do the wires much good and it doesn't do the battery much good either. So just a couple more things to think about. First, we talked about voltmeters and ammeters really quickly before. Now, voltmeters and ammeters need to be placed in circuit diagrams and circuits themselves really carefully. So here's my really simple circuit with a cell and a bulb. Now, I've already made a mistake because if I need to draw an ammeter in, it needs to go in series with this circuit, so it needs to be drawn here. So my improved diagram is going to be drawn like this. So an ammeter always goes in the loop with the component. And we'll talk about why that's the case in the next video. We'll talk about the next one and the one after that. A voltmeter always has to be drawn in parallel with the component that you're looking at. You can't draw it here. So this is an ammeter here. You cannot draw a voltmeter here. It won't work. And we'll talk about why that is the case somewhere else. So a voltmeter always has to be in parallel, and an ammeter always has to be in series. They're quite easy words to remember because voltmeter measures volts or voltage and an ammeter measures amps, which is the unit for current. But that's how I remember ammeter, amps, voltmeter, volts. The final thing to really quickly talk about in this video is something called conventional current and electron current, or electron flow even. Now, when electricity was first discovered, it was well before they discovered the electron. So they didn't know what was carrying electricity, they just knew it was a charged particle. And they made an arbitrary decision. They just thought to ourselves, we'll just say that it's positive. We're not sure. We're going to say it's a positive particle that carries electric current. Now if you've got a battery that's got a positive and negative terminal, a positive charge is going to be repelled from the positive terminal and attracted to the negative terminal, like we talked about in static electricity. So they assumed that the the positive particles would travel from the positive particle here, around the circuit, through the bulb this way, and back to the negative side. Now this is called conventional current, because this is in convention, or as we usually think, how electricity flows. So when we draw a diagram, we imagine that it flows from the positive to the negative terminal. And that's a really odd reason, basically. When they discovered the electron, they couldn't be bothered to change the textbooks, or that's the old wise tale that I've heard, and they just kept it how it was because everyone knew. Now we know that electricity is usually, not always, but 99% of the time, carried by electrons, and electrons are negative. And this is my symbol for an electron, E-. Now, because of this, it means the current actually flows the other way around. The electrons are pushed from the negative terminal through the battery this way and then attracted to the positive terminal. This is the way the electron would go, and this is the way a positive one would go. And this is called electron flow. So if you ever get asked a question, what's the difference between electron flow and conventional current, it's simply that conventional current, the current travels from the positive to the negative terminal because it acts as if it's a positive charge carrying electricity, and the electron flow is how it really happens. So the electrons go from the negative terminal, they're repelled by the negative terminal because electrons, remember, are a negative, and attracted to the positive terminal. So that's all you really need to know about circuit diagrams. I hope that was helpful.